This video is about AM modems. So we would be discussing the construct of AM modulators and demodulators, as well as we would be looking into a Simulink based simulation environment. So in this environment we have a modulator, and then we have two different types of demodulators. The first type of demodulator is basically synchronous or coherent demodulator, and it uses a carrier signal. And the second type is non-synchronous or non-coherent demodulator. So specifically this non-coherent type is based on envelope detection. So some of the discussions would be validated by means of this simulation. Now let us again revisit the AM modulators. The statement says that we can use any DSB-SC modulator as an AM modulator. So all we need is the DSB-SC modulator. By adding a constant DC term to a message signal m of t before modulation, or we can simply add a carrier term to the modulated carrier. So we are basically referring to two separate models. The first model is we have an m of t, and we can give a DC offset, say A, and then we can pass it through the modulator, which is having a local oscillator of cos 2 pi fct, and then we can transmit it. So this is first option. The second option is again we can have a message signal m of t, and now initially we pass it through the local oscillator, which is having the carrier frequency that is cos 2 pi fct. So this local oscillator, we take a thread, give it a gain of A, and then add it to this signal, right? So this was originally DSB SC of T, so let's call this as phi signal, and over here we would have phi AM of T. So both of them are equivalent models for the AM modulators. We can give a DC offset at the message signal, or we can have the carrier added to the message signal after passing through the modulator. Now let us visualize the first type of modulator, which is simulated over here, and herein we have a message signal. This is m of t, and I have used a signal generator block which can be found in the library browser over here. Right, so specifically we have used a sine wave with an amplitude of 1 and a frequency of 100 Hz, and in the first type we give a DC offset to this message signal. So that DC offset is basically a constant signal of 2 volt, and then we use a summation block to sum the message signal and the DC offset. So the output of this summation block is then fed to the multiplier or a modulator. Moreover, we also have a carrier signal, which is again a signal generator, and again we have a sine wave, but now the sine wave is operating at a much higher frequency of 2 kilohertz. So this carrier signal is now threaded to the multiplier. So with the DC offset, the output of this modulator is basically an AM signal, and we visualize this AM signal both in time domain by means of a scope and by means of a spectrum. So for spectrum we are using a zero order hold with this sample time, and then we are using a spectrum analyzer. So note that this is basically a double sideband with large carrier. So let us run the simulation. Now in the scope, the first feed is of the message signal, and the second feed is the DC offset of the message signal coming from here, the output of this summation block. The third feed is of the carrier, and the fourth feed is AM modulated signal. So let us visualize these results. So this is our message signal which is having the peak value of +1 and the negative peak is at -1. So we give a DC offset of +2, so this 1 goes to 3 here and this -1 goes to +1. So now the offset message signal is now oscillating between +3 and 1. The carrier is operating at a higher frequency, this is this is at 2 kilohertz. And finally, if we modulate this signal with this signal, now we have the amplitude modulated signal. And the important thing is that we have given enough DC offset that the lower value is above 0. So right now the maximum is at +3 and the minimum is at +1. On the lower side of the envelope, -1 and -3. So we do not have the zero crossing of envelope. It is always positive. So over here the modulation index, which is the peak value of the message signal, which was +1, is divided by the amplitude of the carrier, which is basically +2 over here. So we have the modulation index, which is 1 by 2 and 0.5. So over here the modulation index is 0.5. Also the spectrum. So in the spectrum, this is the carrier that we have mentioned, and these are the side bands. This is the upper side band, lower side band, and the carrier. So the carrier is at 2 kilohertz. The upper side band is roughly at 2.1 and the lower side band at 1.9. Now in terms of simple circuits, over here we have the local oscillator, which is operating at omega ct, which is higher frequency, and then we have a low frequency signal. Then we have a diode, a resistor, then we pass it through a band pass filter, and eventually we have the output, which is in terms of an AM signal. So in terms of mathematics, this V of t is nothing but from KVL, a combination of M of t plus C cos omega ct, and then W of t is basically a characteristic of diode, which is being switched by means of this cos function, the local oscillator. And if it is triggered with this cos function, so the diode would have a behavior which resembles a square wave. So this square wave would have a time period of t naught. So if this is periodic, which it is, so we can use Fourier series, and particularly we have used trigonometric Fourier series over here, and we expressed that by means of an a naught, and these are an terms, and we have the harmonics omega c, 3 omega c, 5 omega c, t, and so on. So because of this even symmetry around the origin, so this means that the sine terms in this Fourier series are no more there. So you can study this further in chapter 2 of the textbook. So multiplying these two together with W of t would yield V of t, that is voltage across this resistor, and these are represented over here by means of this expression. So next we can extract out the signal which we want to transmit. Note that we want to transmit an AM signal at omega ct. So we stack all the frequencies which are at omega c together, and we separate all other frequencies. So in other frequencies, these two terms are basically low frequency, and these other terms would be high frequencies. So but we need actually to send a signal at omega c, so we will be sending this by means of a band pass filter, and we would reject this with the same filter. So this discussion was about a switching modulator, where we have this diode which would act as a switch, and eventually we are creating an amplitude modulated signal operating at mega CT. Now when it comes to the demodulation, we have two possible options. The first one is coherent modulation, coherent demodulation. This is the first option. And the coherent demodulation, we need local oscillator both at the transmitter side as well as at the receiver side. So if we are having an antenna which is basically receiving antenna, so a signal was sent and we receive it, and this is the signal that we receive. So we pass it through a DSB-SC demodulator. So the outcome of DSB-SC modulator is basically 1 by 2 A plus M of T. Now this A is added because initially in the modulation itself we added A. So in order to remove this A, whatever circuit we have, we can use a capacitor in series. So eventually we will get 1 by 2 M of T. But do note that coherent method of demodulating an AM signal which is having a carrier is not a wise thing to do, because we were doing it already for DSB-SC and that was simpler. So while we are having more power at the transmit side and still using coherent modulation, so this is not very wise design to have. Let us now look into the simulation of this coherent demodulation. So the coherent demodulation is represented over here, where this is our modulated signal, that is phi am of t, and this is basically received at the receiver side. So this is our receiver, and we again use a multiplier, that is the product, which is having two number of inputs, and we use the same carrier which is operating at 2000 hertz, and this is basically a signal generator block. This is in exact sync or agreement with the transmit carrier. So after that, as per the DSB-SC discussed previously in this link, we have a low pass filter. Specifically, this is analog filter design, and we have used a Bessel low pass filter of order 8, and we have set the pass edge frequency in radians per second to 2 pi 500, right? And then we have put the output of this signal to the scope. Moreover, we have used a zero order hold or a sample and hold technique with these parameters, and then we have used a DC blocker. So DC blocker is, we have mentioned previously in the discussion that we needed to remove the DC offset. So this is our DC blocker. So we are using basically a discrete time version of the DC blocker, and we are having infinite impulse response. So since we're using the discrete time block, so that's why we are using this zero order hold. And then the output of this DC blocker is then fed to signal waveform. So again, let us zoom this part of the demodulation. So multiplier, carrier, the filter, and then the DC blocker, and this is the output. Now in the scope, the first feed is of the message signal. The second feed is the output of this demodulator, but before the filter. That is, whatever we are getting, we are multiplying with the carrier again, and this is our second feed. So in the third feed, this is basically the output of low pass filter, and finally the fourth feed is coming from the DC blocker, right? So let us visualize these results. So the first signal is the message signal. The second signal is coming from here in this branch, and this is simply a multiplication of the input with the carrier. So from the input we were having a cos function, and from the carrier we have another cos, so we have a cos square function. So that is why this is the result of that cos square function, and this cos square function has a low frequency, and within that low frequencies we have some high frequency oscillations. So we can filter out the high frequencies, and this is being done over here in the Bessel filter. So if we filter out the high frequency, so we have a signal which is basically oscillating between +1 and +3. So we have a signal which is having a DC offset. So you can observe that the envelope is almost having the same shape as the message signal, but the output of filter is a little bit different. That is, this peak has a time delay to this point. That is, this is now shifted over here. And again, this is the characteristic of the filter that we use, and that filter basically introduces a delay. Anyways, we have a signal at the output of this filter which is having a DC offset of +2, right? So that DC offset is basically removed by this DC blocker, and now this will come back and we would have a signal which is between -1 and +1. So this is the signal that we desire to achieve, and we have a linear phase shift, so this is a distortionless transmission, so we can use time advance or a time delay property to get back our original information. But again, note that using carrier at demodulation is not a wise thing to do, so we need to look into some non-coherent methods. So that is why we move towards non-coherent methods of AM demodulation. And among the non-coherent methods, the first method that we have is basically rectifier detector. So this is the rectifier detector. We have phi a m of t represented as a plus m of t cos omega ct. So in the rectifier detector, we have a diode, a resistor, much like the transmitter side. Now we have the same kind of a setup. Previously we had a band pass filter. Now, because we are interested in low frequency, this is the demodulation. So eventually we need this somehow to link with the message signal, and the message signal is at low frequency, so we're using low pass filter. Then we have a DC block, and eventually we're getting the message signal in some form. So starting with the AM signal, so this is our AM signal, right? We have an outer envelope, and within that envelope we have the carrier. So this is basically received over here. Now after passing through diode, we have this waveform where all of this part is basically cancelled, and you have a plus m of t as an envelope, and within that envelope we have these oscillations. So over here you can observe that we have basically a low frequency content, and within that low frequency content we have high frequencies. So we can extract out the low frequency by means of a low pass filter. So this is something that we have done over here, right? So we have extracted out low frequency and removed the high frequency from the filter. So note that the lower end, this part, is basically linked with the low frequency and hence the message signal, which is overall a scaled version of the envelope. So as we have this waveform before the capacitor, so this capacitor would remove the DC offset, that is, it would remove this A. So eventually if we remove the A by means of this capacitor, we would have 1 by pi m of t. That is a signal that we desired, or that is the one that we initially modulated. So this is the mathematical model of the same rectified detector, and again this signal is being multiplied with the diode waveform, and that is W of t, which is again a Fourier series, and that Fourier series, trigonometric Fourier series, is represented over here. So multiplying W of t with AM signal, we have this equality over here, and then we extract out the cos square term, and we leave the remaining terms over here. So why we have extracted out the cos square term? Again, because cos square of theta is 1 by 2 plus 1 by 2 cos 2 theta. So this is something that we have done. So there was a 2 over here, and this is basically being removed. So eventually we have this term which is around the message signal, and we have a DC offset, and these are all other terms operating at different frequencies, so we are not interested in these. So these high frequencies are basically rejected by the low pass filter, and eventually we have 1 by pi a plus m of t. So this is the reason we had this 1 by pi represented over here. So this is after the low pass filter, so this is the thing that we'll get. So after the value of a blocked by capacitor over here, so eventually we would have the message signal that we desire. So this was rectifier demodulator. Now let us look into the second method of non-coherent demodulation of AM, and this is actually one of the simplest methods that we come across, and this is something that we call as an envelope detector. So this envelope detector contains a resistor, a capacitor in parallel, then we have a resistor, and after that again we would have over here a low pass filter, and eventually we would have a capacitor in series, and then over here we would have across this resistor an output which would be related with the message signal m of t. So this is actually the complete circuit of an envelope detector. So as the name suggests, we are basically detecting the envelope of the message signal. So note that the phi am of t, this is basically this blue signal that we'll get. So in the positive cycle, the diode would be forward biased, and we are going to charge the capacitor. So the capacitor would charge. But when we are going downward over here, the diode would be reverse biased and the capacitor would discharge across this resistor. So we would have the charging and then discharging of capacitor continuously going on, right? So as mentioned, the diode would be on for some time and then the diode would be off for another instant of time. So what would be the charging time and discharging time? So this depends on tau, right? And it is linked with 1 over 2 pi the RL or resistor and then capacitor. So we have two types of resistances. The first one is load resistance RL, and the other one is source resistance. So we have to make sure that we set the resistor and capacitor in such a way that we can have an appropriate charging and discharging. For example, now by means of these expressions, we have mentioned the charging and discharging of the capacitor. So this says that the charging of capacitor must be, or the time constant tau c must be much less than 1 over frequency of the carrier, whereas the discharging of the capacitor should be much less than 1 over bandwidth of the message signal, and it should be much greater than 1 over frequency of the carrier. So over here we have two scenarios which are actually undesired. So in the first case, part A, we have TD which is too large, that is the discharging time is too large, right? So we have these oscillations which are from AM signal, right? So the capacitor is basically charging discharging very slowly, right? So this is discharging very slowly. So if this is discharging very slowly, so this means that the envelope would not be detected and hence the purpose would be killed. So we have to fix the discharging time by adjusting the values of load resistor and capacitor. On the other hand, if the discharging time is too fast, that is TD is too small, so we are having a charging over here and then eventually we discharge very quickly, and then we charge again and then we discharge. The envelope is this one, but we are not tracking it. We are actually decaying to zero and then going up and then again decaying to zero and then going up. So this is quite undesirable. What we need is basically this kind of a phenomena where we charge and then discharge, charge, discharge, and so on. So at V output of t, we would have a waveform. So this let me call as V output of t. So this would be actually of the shape and so on, right? So it has low frequency and then it has high frequencies which indicate these ripples. So we reject the high frequency by means of low pass filter. So eventually we would have a waveform again which would have some kind of this behavior, and then by means of this capacitor we can remove the offset, so we would have the original signal. So this is all about the envelope detector. Next, in simulation we would be using the envelope detector, however at the system level by means of signal squaring method, as compared to a circuit level design which includes diode and capacitors. The envelope detection of AM modulation is performed over here, and again this is a system level that requires signal squaring and low pass filtering. So this type of envelope detection is described in this video link. Now let us just focus on the envelope detection for the time being. And over here, this is our received signal, that is the phi AM of t that we receive, the AM modulated signal. And the envelope detection actually works on discrete time signals, this type of envelope detection. So we use a zero order hold with this sample time, and next we use a squaring method, then we use a gain block having a gain of 2, then we are using the FIR decimation with dial out parameters, FIR filter coefficients, decimation factor, and so on. And next we have the low pass filter with these parameters. So next we have the square root function, that is sqrt, that is a sine square root. So all of this is basically available in the Simulink using this command. So at the output of this envelope detector we would have a positive pulse with some oscillations having high frequencies. So the high frequency oscillations are basically removed from the low pass filter. Then we use a sample and hold. Eventually we use a DC blocker. Again we use an infinite impulse response DC blocker, and then we portray the output of this DC blocker to the signal waveform. So let us visualize the results. Now herein the first waveform is of the message signal. The second waveform is basically the demodulation of a coherent demodulator that we have discussed previously. And the third waveform is basically the demodulation using a non-coherent method, and specifically envelope detection. So you can observe that in the envelope detector method, the phase shift is quite high. Previously this was the message signal, but because of low pass filter we have this phase shift. But in the envelope detection we have two different types of filters. The first filter is used within the envelope detector and the second is outside the envelope detector. So hence we have multiple phase shifts. So that is why this message signal, when we receive it, the peak is basically shifted or delayed quite a lot, but it is consistent, that is we have a linear phase delay. Moreover, you can observe that we have the peak value between plus 5 plus 0.5 and minus 0.5, so we can give a gain of 2 to eventually get a plus 1 and a minus 1 kind of an oscillation. So in a nutshell, if we give appropriate DC offset to the message signal using envelope detector or by using any other non-coherent modulation demodulation scheme, we can actually recover back the original signal. So following were the references that we have used in the construction of this video. Thank you.